In this lesson, we're going to continue our look at acyl substitution reactions on carboxylic acid derivatives, focusing on reactions where hydroxide is the nucleophile. In a previous lesson, we established the order of reactivity for the major carboxylic acid derivatives. The general trend was that compounds with a better leaving group were more reactive. The exception was that carboxylic acids were the least reactive, despite having a better leaving group than an amide. Carboxylic acids typically don't undergo simple, uncatalyzed direct acyl substitution reactions. Hydroxide is a pretty bad leaving group, and for most reactions, the equilibrium is simply going to favor the reactants over the products. In this example, an attempted reaction of a carboxylic acid with chloride fails. The chloride nucleophile is simply a better leaving group than the hydroxide, pushing the equilibrium to the left, favoring reactants. But what would happen if a carboxylic acid were treated with a nucleophile that was a worse leaving group than hydroxide? In this example, we see a carboxylic acid reacted with NH2-. The expected acyl substitution is depicted on the top portion of the reaction. Because hydroxide is a better leaving group than NH2-, we would expect the equilibrium to favor products, going to the right. And this is absolutely true. The problem is that another, much faster reaction competes with the substitution. Carboxylic acids are acidic. And remember that strong nucleophiles are also strong bases. Treatment of a carboxylic acid with NH2- can result in a simple acid-base reaction. The carboxylic acid is deprotonated to form a resonance-stabilized carboxylate anion. The products from this lower acid-base reaction are considerably more stable than the products from the upper acyl substitution reaction. This is mostly because the negative charge is stabilized by resonance in the product of the acid-base reaction. The acid-base reaction is favored both kinetically and thermodynamically over the acyl substitution reaction. This essentially prevents the acyl substitution from occurring. Carboxylic acids are unreactive in simple, uncatalyzed acyl substitution reactions because any nucleophile that's strong enough to displace the hydroxide is also basic enough to simply deprotonate the carboxylic acid. If you stop and think about it, using hydroxide as a nucleophile in any acyl substitution reaction is going to result in the formation of a carboxylic acid. All carboxylic acid derivatives can undergo base-promoted hydrolysis. Hydrolysis is a broad term that refers to any reaction in which water cleaves a functional group. Here we see an example of an amide undergoing base-promoted hydrolysis to give a carboxylic acid. If we gauge the reactivities of both the starting amide and the product carboxylic acid based purely on the quality of the leaving group, then we would expect this reaction to fail. NH2- is a worse leaving group than hydroxide, and that means the reaction should favor the reactants at equilibrium. However, this reaction does in fact work. The figure below explains why. The initial acyl substitution would result in the formation of a carboxylic acid and NH2-. We would expect this equilibrium to greatly favor the reactants. The negative charge is simply more stable on the oxygen on the left side than on the nitrogen on the right side. But remember, this reaction is still under equilibrium. Even if the products are greatly disfavored, some product will form. The newly formed carboxylic acid now has two potential reactive pathways to follow. One potential pathway is the reverse acyl substitution, in which NH2- would displace hydroxide to reform the starting amide. The second potential pathway is the simple deprotonation of the carboxylic acid to form a resonance-stabilized carboxylate. As we just saw, the acid-base reaction is favored both kinetically and thermodynamically over the acyl substitution. The overall reaction will ultimately lead to the most stable products possible, in this case, the carboxylate, which can then be protonated with an acidic workup to give a carboxylic acid. Under these basic conditions, the carboxylate serves as a thermodynamic sink, all but preventing the reverse acyl substitution reaction and allowing the hydrolysis of the starting amide. Nitriles can also undergo base-promoted hydrolysis. As you can see in the example, the reaction can form either an amide or a carboxylic acid. The reaction often favors the formation of a carboxylic acid, especially at high temperatures and when an excess of base is used. If we look at the mechanism, we see that it's mostly just proton shuffling. In the first step, nucleophilic hydroxide attacks the electron-deficient carbon of the nitrile, breaking one of the existing carbon-nitrogen pi bonds. At this point, we simply need to remove the proton from the oxygen and place protons on the nitrogen to form the amide. The imine anion formed from the first step is negatively charged and strongly basic. The nitrogen is thus protonated by water to give a neutral, uncharged intermediate. Because the conditions are basic, we can predict that the next step should be deprotonation of the oxygen. Hydroxide removes the hydrogen from the oxygen to give a resonance stabilized anion, which is then protonated by water to give an amide. Depending on the specific reaction conditions, the amide can then undergo base-promoted hydrolysis to give the carboxylic acid.